thanking the organizers very much for giving me the opportunity to talk, and also for giving me the option to give this talk remotely on short notice. I would be much rather be with all of you, and I'm really sorry that I cannot be there. So talking about black holes at high redshift, of course, we need to understand what actually we are meaning about this when we say this. And so just considering, no, of course, cannot advance and have to stop share and share again, as usual. Sorry about that. Okay, this works. So by using facilities from the ground and also from space, like the Hubble Space Telescope in the past decades, we've already learned a great deal about how the general properties of galaxies evolve with cosmic time. So for instance, we have learned that there has been a peak of star-formation density at redshifts 1 to 3, typically called the cosmic noon. And the recent winding down of star formation activity has been accompanied by a decline also in molecular gas fractions, while at the same time, galaxies have been accumulating mass and grown in size considerably over the past couple of billion years. Now, interestingly, it has been pointed out that the black hole accretion rate density, which in this case has been constrained through detections of X-rays, seem to have a very similar shape compared to the star formation rate density, as also shown in the famous plot from Marder and Dickinson in 2014 here in the bottom right. And this, together with the fact that in the local universe, massive black holes seem to have a tight correlation with several properties of the host galaxies, like here, for instance, indicated through the bulge mass in this plot to the left, has indicated to people that there has been a tight co-evolution of the growth of galaxies and black holes over cosmic time. Now, I will come back to this black hole accretion rate density also based on these X-ray detections a little bit later on in the talk. But I want to say that already in the couple of last years, recent detections of black holes in excess of millions to billions of solar masses, already at redshift 6 or 7 or so, have put forward important questions about how galaxies actually grow and how the black holes grow, and at which point in time this coevolution that has been suggested through these local observations in the past billion years might break down also in terms of seed properties of black holes. And of course, we will hear much more about this in talks later by Priya and by Kohei as well. Now, to highlight how really JWST is pushing our understanding of these early black holes, I just want to show here what are the instruments that we have been using to learn about these general galaxy population properties that I've told you about. And a lot of this has been done, of course, with ground spectroscopy, with IMA pushing to somewhat higher redshift, and of course also HST. But really the revolutionary capability of JWST is to now push into the first billion years, well into the first billion years at a time where we think that the first stars, the first galaxies, and of course also the first black holes are growing. And to show you that this is not just some pretty schematic, I'm showing here a plot that shows the bolometric luminosity as a function of redshift. And you can see in this brown shading what has been known before James Webb. And now in these blue symbols, the diamonds and the stars, you can see what has been discovered with JWST in these first few years of observations. And so it is very clear that with JWST, we can push to much lower luminosities in terms of these actively accreting black holes, but we can also push towards higher redshift. And therefore, JWST is really opening up a completely new discovery space and a new space where we can learn about early black holes and, of course, also about their connection and coevolution with their galaxies. And preliminary numbers that we have from various teams working on this across the world is that there seems to be an incidence of about 10 to 20% or so of galaxies that host a low to moderate luminosity AGN at these early times. Now, how do they look like? I'm showing here some images from some different teams. And if you go through the literature and look for some images from Neil Camusot for these sources, many of them are very similar. So what you can see here is that many of these sources appear extremely compact. You can see in some of these images this little star shape, which is basically an imprint of the PSF indicating that we have light from a point source coming towards us here. Some of these galaxies tend to have some bluer fluff around them. These might be accreting objects or interactions, minor mergers. And actually this merging activity or accretion activity might be what is actually fueling this activity also of these black holes. But in general, you see that they are all very compact. Some of them appear to have red colors, and I'm sure that this is a topic that has already come up in the meeting and also will be discussed more later on, I'm sure also by Dale after my talk. Now, this is how these objects look like in imaging, but what are their spectral properties? Here I'm showing one of our most beautiful examples. This is GS3073, redshift 5.55, just 1 billion years after the Big Bang. And this is an object that was observed within the Garniff survey, which is the near-spec integral field spectrograph GTO team. And what you can see in this high-resolution spectrum of the object here is that we have beautiful broad-line regions. So we have gas that swirls around the black hole with high velocities in the hydrogen and helium lines. We also see indications for high ionization species such as helium-2, we have argon-4, and even some coronal lines in this case. You can see again in the image that this is fairly compact. We see again this PSF shape and some satellites that are possibly in interaction or accreting onto the system. But even though the source lies in one of the deepest Chandra fields with more than 7 megasecond integrations, we have no X-ray detection for the source. So this is, of course, just one of many, many HEN, as you've seen, that have been discovered since, and many groups across the world have been working on this. And of course, with these wealth of spectral lines that you can see here, we can constrain a plethora of physical properties, not only of these black holes, but also of the host galaxies. But of course, in this talk, we want to focus on the black hole. And one of the key quantities that we can determine with these spectral shapes that we see here is the black hole mass. And so just to briefly illustrate how this is done, we can use the spectral shape of the broadline region. This is indicated here in purple. And then we typically use at high redshift what is called a single epoch calibration method. And I'm showing here an example formula from Amy Rain's paper. And this is highlighting how here the black hole mass is related to the luminosity and the line width of these broad lines. And so therefore can be used to determine the black hole mass. In the case for the object T, we find about 10 to the 8 solar masses. Okay. So we have these methods, and what do we find when we apply them? I'm showing here examples from the Uncover team and from the JWST team, worked by Kokorev and Jules Farlis. And what you can see in these plots that show the black hole mass as a function of host galaxy stellar mass is that these colored points, which are different JWST detected HEN, are at fixed stellar mass, much more massive than galaxies, black holes for galaxies in the local universe. And this is indicated here by these local relations, the green line in the plot to the right and the black lines in the plot to the left. And you can see that all of these detected sources are several orders of magnitude above these local relations. This has been investigated again by many teams. You can see that there are a wide range of references in the listing here. People looking with various data sets and different surveys into these properties, although there are also some works that investigate whether there are any potential biases in making these measurements, like the recent work from Lee, for instance. Now, one question, of course, that comes up is how reliable are actually these high-redshift black hole masses. And in the next few slides, I want to make 2 points touching back on this. And so first of all, I want to show this result here by the Gravity Plus collaboration. So this is not JWST, but actually using the VLT and interferometric ground, interferometric mode from the ground. And this is a really exciting result, which is the first dynamical BLR measurement at redshift 2.3. So this might sound like a low redshift now to some of you, but actually this is just 2.8 gigayears after the Big Bang. So in time, this is very close to many of these sources that we are studying. And they made this dynamical black hole mass measurement and compared it to different single epoch calibrations that I've been talking about before. And what they find is when we look at H alpha, is that indeed it's possible that these single epoch measurements based on H alpha might have a slight systematic bias in the sense that the black holes that we measure with JWST could be overestimated in their mass by maybe a factor of up to 2. Now, it's interesting to point out that for other lines that they also investigate, this bias could be much larger. And of course, this is only one object, but I know that there are several more objects on the line in a similar redshift range, where for H alpha, they find roughly about this factor 2. And of course, this is not too bad, and it's actually extremely exciting that we can make these accurate measurements now of these black hole masses so early in time. Now, another topic that is connected to this will become clear in a few seconds is the lack of X-rays that I mentioned earlier on, which is associated with these early black holes. Again, here I'm showing plots from different teams. We look at the bolometric luminosity over the X-ray luminosity as a function of bolometric luminosity. And these solid lines that you can see in these two plots here show typical relations that we have in the local universe and find for active black holes. And now most of these color points over here and here, these yellow and some of these other points are HEN that we have detected with JWST. You can see that most of them are showing lower limits. So the majority of these black holes that we are finding are much, much weaker in X-rays than what we expect from the local population. So this is what we see really for many, many of these sources. However, there are, of course, a couple of HEN that are X-ray detected. First of all, there are all of these HEN that have been selected through X-rays and have been followed up with JWST. For instance, the work by Michele Perna from the Galaxies team. But then there are also sources that are now discovered to be HEN and that also show X-ray emission. And I'm sure that also on this topic we will hear a bit more in the talk by Dale about the sources that he has discovered, and also later on by Priya about UHC1. Now, what's the reason for this X-ray weakness, however, for the majority of the sources? So first of all, this is not just due to individual objects. Here on the right-hand side, I'm showing stacks of several tens of objects from the work by Yue and Anana. And you can see that also here in the stacks, there are no detections of any X-rays. Now, of course, the question is this some sort of intrinsic X-ray weakness that we observe in these objects? Could there be absorption perhaps of the X-rays, or are these objects maybe not actually black holes? And we have some work here led by Roberto Maiolino, who I know is in the room with you, investigating this in great detail. And we think we can be pretty confident that most of these sources are actually HEN. Of course, we have these beautiful spectra, like what I showed you in the beginning, where we have multiple indications clearly showing us that we're looking at an actively accreting black hole. There might be some individual cases, just a few percent, where maybe supernovae could mimic a similar signature, but this could only be a minority in the cases that we see. And so in this paper, we focused on these different investigations of what the X-ray weakness could be due to. And one line of thought is that it could be that really the corona has not really developed yet, and so the X-rays are very weak, similar to some narrow line C1 galaxies in the local universe. But what we're actually favoring is that the X-rays are indeed absorbed through very dense medium immediately around the black holes. And this could be accomplished, for instance, through a very high covering factor of the broadline region that has densities that are high enough to actually absorb these X-rays, and this is discussed in more detail in the paper. And what is really interesting about this scenario is that, of course, the different geometry of the broadline region would again indicate that some of these local scaling relations that we are using are not entirely adequate for these systems at higher redshift, because in this case, then also we would have to downcorrect the black hole masses maybe by a factor 3 or so. However, what I want to impress upon you in this context is that even if we have these potential sources of systematics that may lead us to overestimate the black holes, maybe even up, combined with these different scenarios by up to a factor of 10 or so, we are still far away from where local HEN lie. And I just want to show you this again here on the plots to the right. You can see here these JWST discovered HEN in yellow and in blue, and the local HEN in red. And so even if you have to change here the black hole masses by an order of magnitude, at fixed stellar mass, these JWST discovered HEN are much more massive compared to the host galaxies when we compare this to local HEN. Now, what is really interesting in this context as well is that if we look at different tracers that characterize the host galaxies of this object, specifically if we go to dynamical estimators such as the dynamical mass or also the central velocity dispersion, then we see that this picture is changing. You can see this in the bottom right plot here. Now these JWST discovered HEN move much closer to the local relation. And this indicates that we do not just see an extremely peculiar population of high-redshift HEN, so to say, the upper envelope of black hole mass that we're seeing there, but actually these objects are typical in several of their properties compared to local HEN as well. However, they might have, for instance, not been so efficient in forming stars yet in the short amount of time that the universe had, or maybe we are now actually probing this specific region in time where there is not yet this exact coevolution, and these black holes are already born relatively massive. And yeah, Priya will discuss this in much more detail later on. Now, what is also pointing and hinting towards this scenario where we have this extremely high central densities around the black holes is this very exciting finding now of several groups that there are cases where we see absorption features in the broad lines in this HEN. And this indicates that we have extremely high densities, greater than 10 to the 8 particles per cubic centimeter. I'm showing here some examples by Eiger and Fresco and by Sears, and of course, Dale may discuss this in much more detail later on, so I don't want to say too much, but I just want to point out that the numbers that we have so far from these works, so what you can see here, but also work by Ignaz Jules-Squalis, by Maiolino and Wang, is that up to 10% or maybe even more of the so far JWST discovered broadline HEN that we see at high redshift might have these features. And this is much higher than what we see in local HEN, and could again point, as I mentioned earlier, just to a different shape and geometry of the VLR and extremely high nuclear densities in these very early and compact systems. Now, all that I've been saying is focusing on HEN that are detected through their broad lines, but of course we know that there are also HEN that are obscured and very typically rely on narrow line ratio diagnostics to identify them. Now, many people have noticed, many teams early on, already last year, is that when we consider what has typically been used in the local universe, such as the BBT diagram, which is shown here in these two plots, where typically in the local universe HEN are located in this upper right part of the diagram. When we now consider the spectral properties of these JWST discovered HEN, we see that they are on the boundaries between HEN and star forming, actually in the star forming regime. So these are the red sources in the left plot and the blue and yellow sources in the right plot. Now, this has been shown observationally through these works and a couple of other papers, but it's not actually a surprise in the sense that models have already told us over many years that this is a scenario that can happen when we go towards lower metallicity systems. And this is indicated by some models here by Nakashima and Maiolino in the panel to the right, but there are similar works that I'm listing in the references at the bottom. And here, when we go from these little red stars to the blue stars, we go down in metallicity, and you can see how this locus of HEN is actually shifting from the top right to the bottom left. So this tells us that this specific diagram is no longer effective in selecting narrowline HEN at high redshift, and so of course people have been starting to investigate what are potential other diagnostics that could be used, and I just want to show a few examples in the next couple of slides. One diagnostic that we've been looking at for this object 3073, this beautiful HEN that I showed you earlier, is the helium-2 line. And here we have a diagnostic in the left panel that has been suggested by Shiraz and Brinkmann already in 2012, and has been shown to hold for many low redshift HEN. And what we can see for our high redshift object here is that indeed this diagnostic seems to be able, even for mixed metallicity, which is going here again from higher metallicity in red to low metallicity in green, to be effective in still discriminating between HEN and star-forming galaxies, because at least in this diagram, also the models are well separated. However, unfortunately, we only have a few objects where we can really detect this helium-2 line. And so for the majority of sources, this might not be applicable. Something else that people have been looking into is using line ratio diagnostics of UV lines, specifically for galaxies that are observed with the prisms part of the near spec. And this is work here from the Jason by Jan Scholz. Again, here we are learning from what people have been doing already in the local universe over the past years and decades, and now trying to apply these diagnostics to these high-redshift AGN. Another interesting line that people have been looked at now is the Aurora 034363. This has been detected in many of the JWST discovered AGNs so far. In fact, there have been already a couple of papers using this as well to investigate metallicities. And in this work by Giovanni Mazzolari from earlier this year, they are proposing 3 different diagrams that use the Aurora 03 OH gamma ratio as a function of other line ratio properties. And what you can see here in the left plot is in contours local universe galaxies, AGN in red, Sachem galaxies in blue. And then in the different colors, you see several AGN at low and high redshift in red and Sachem galaxies again in blue. And to the right, we see the same plot now just in model space, here focusing on models from Nakashima and Maiolino and from Feldre. Again, AGN in red and galaxies in blue. And you can see that this upper part of the diagram is really populated only by these AGN models. And this gives us hope that we might use diagnostics that involve this Aurora line to effectively single out AGN-dominated systems in the early universe. So these are some of the avenues that people are going into selecting these narrow line sources early on. And I want to go back a little bit more to some of the spectral properties of some of these objects. So just briefly here, I want to show again this plot of 3073 that I showed earlier. And we have observed this object not only in high resolution, but also in low resolution with the prism. And I briefly want to point your eye towards the H-alpha and N2 complex here. You can see that we have a detection of nitrogen 2, but this is very weak. Mind that the log scale here, the flux scale here is in log space, so this is a very weak line, but it's clearly detected. Now, if we go to the prism spectrum, and this is work that has been led by Shihan Yi, together with the Ganev collaboration, you can see that we see very strong nitrogen 4 and nitrogen 3 lines in the UV. And this points toward a chemical stratification in the source, and not only from the chemical perspective in terms of N over O, but also in the densities that these different lines are tracing. So we have a high density, high N over O region, and then we have a lower density, low N over O region. And this is indicated in the plot to the right. Our object 3073 is these 2 bright red symbols that you can see here. And in the UV lines, we have a very high N over O ratio. In the optical lines, instead, we are more or less consistent with what is also observed in local H2 regions in the Milky Way, which are these other white points that you can see here. Now, there have been a couple of other objects observed with these peculiarly high N over O ratios that are indicated in the plot here. Also GNC11, which is this maroon point over there. And of course, people are investigating different scenarios that could explain these abundance patterns. And they might be consistent with supermassive stars, with wind from Wolf-Rayet stars, etc. But what is really interesting is that this is also very similar to second-generation stars and globular clusters in the Milky Way. And this, again, could point towards this scenario where we have these extremely compact environments around these AGN, where we have this very intense star formation and also accretion onto the black holes.
Hannah, sorry to interrupt. We have about 30 seconds left.
Yeah, all right. I will speed up and show the beautiful GNC11 spectrum, highlighting here the nitrogen lines that I just mentioned, but also other spectral properties that we also discussed before, indicating extremely high densities of 10 to the 6 or 10 to the 10, very fast outflows and high ionization. And here for the specific object, we are really pushing into a regime of very early times in relatively low black hole mass, where we can start to finally constrain different formation scenarios. But of course, this is something that will be covered by Priya in more detail. And therefore, I just want to say a few more words in these last seconds about another topic connected to black hole growth, but on a somewhat different level, which is potential merging of black holes. And so here we have seen some cases in the JADE survey where we see in these BLR shapes not the typical line decomposition that we expect, but some more peculiar shapes. And this could indicate, and is in these examples consistent with, a second lower mass black hole. Now, these observations with the MSA, of course, do not have coverage, spatial coverage of these sources, and so the interpretation can be a bit more difficult. And so we have been very excited within the GANEF survey with the IFS to detect the galaxy redshift 7.15, where we see an offset HGN, here indicated in the broad line in H beta, which is offset by about 600 parsecs from another galaxy, where we find indication based on the auroral 3 OH gamma ratio that it hosts a narrow line HGN. And so we believe that systems like this have a dynamical friction time based on the mass properties of maybe 100 to 200 million years. And so will merge in the foreseeable future. This will be able to detect, of course, with facilities such as LISA. And this might actually also explain, of course, these activity that we see in the black hole gas that is efficiently channeled towards these two black holes that are spiraling together. And this is extremely, of course, interesting to study, to learn about alternative growth channels for these black holes. Now, I think I have to skip this. Just wanted to highlight here how powerful the IFS is really in helping us to learn not only about black holes, but also about their host galaxies. So let me know if you want to know more about this, and I can go back to the slide later. But this is also why we are extremely excited that we have a Cycle 3 large program coming up, where we can use the integral field spectrograph to study in much more detail the not only black hole properties, but also host properties of 25 AGN, where we want to learn, of course, about the dynamics, masses, look for more mergers, constrain the impact that the AGN has on galaxies through outflows and feedback, and also constrain possible contaminations, for instance, through supernovae. And so this is very exciting. And with this, I'm coming to the end. Sorry for being slightly over time. I hope I could show you that JWST enables us really to push the boundaries towards lower luminosities and higher redshifts in our quest to understand early black holes. And many of the properties of these early black holes are surprising and still need to be fully understood. For instance, the extra weakness, these absorption features that we see in some of these sources, and also other things that I haven't touched upon now in this talk, for instance, the lack of very strong or ubiquitous outflows associated with this black hole activity. And I think it's really extremely exciting for us in the field that within the next cycle of JWST observing time in GEO and GTO, across more than 6 programs focusing only on the near-spec integral field spectrograph, we will have more than 200 hours devoted to studying galaxies and the black holes in the early universe. So I'm sure we will be able to learn much more about this interesting field in the next couple of years. And if you're specifically interested in black holes, I finally just want to advertise that we have a conference coming up next year that we're planning in Cambridge in September. And so if you're interested in this topic, please keep a lookout for any advertisements on this. And with this, I want to thank you very much for your attention. I'm happy to take any questions.
So just ask all questioners to please say your name too, full name before your question.
Hi, Hannah. Thanks for a great talk. This is Joe Hanawi. At low redshifts, low luminosity quasars, which have smaller black holes, actually have a harder rest UV spectrum, and that's also expected from theory, from the structure of their accretion disks. What surprises me about all of your AGN is that the high ionization lines are either weak or not there. And I just wondered if you could comment on that absence and what you thought about it. So carbon-4 doesn't appear to be there. That's one line I'm focusing on particular, but also, I guess, nitrogen-5. So they look quite different than what we're used to seeing from quasars.
Yeah, so we do see some, thank you for the question, we do see some of these high ionization lines in some of the sources. And so one of these examples is, of course, GNC11, what I'm showing again here. I hope you can see that I switched the slide. Where here, for instance, we have this detection of the carbon-4. I think we still, this is one of the most luminous sources that we have. And also the other case of CO3 C is extremely luminous, where we also see some carbon-4, but it's not, as you pointed out, not as bright compared to nitrogen when we look at the ratio to oxygen. And I think one point is that we still need a lot of integration time to really go into these potentially somewhat fainter lines and really discover them. So there might be some more sources that we can discover in this respect in the coming years, and just by looking longer at these objects. And on the other hand, I think people are still trying to understand what exactly could be the scenarios that explain this enrichment in having these strong N over O and more normal carbon ratios, like for instance, some of these scenarios that I sketched here. Now, what the typical explanation is in a connection to these low redshift Seafords, I wouldn't be sure, but I'm sure in the room there might be some experts that have some ideas about that. So I'd be curious to hear what you think and what others are thinking.
Thank you.
I just wanted to comment that most of these...
Say your name too, please.
Roberto, I don't know if you know him, Maiolino, okay. So in a lot of these agents, a large fraction of many of the differences that we see are actually seems to be due to metallicities. So many of the high ionization metal lines are simply suppressed because of lower metallicity. It goes in the BPT diagrams, in the UV diagrams, and including the carbon-4, which anyhow often has a physical profile, so you have to convolve with the absorption. So it's not so simple to compare directly with the normal quasars, which are very enriched. Yeah, but that's much more massive systems, which are already have reached the very high metallicities in the maturity. So I'm not so surprised in this respect. We are talking about systems which are orders of magnitude smaller in black hole mass and in stellar mass. So it's not surprising that they are, have very lower metallicities. We see lower.
Thanks. Hi, Hannah. Thanks for this wonderful talk. This is Rachel Somerville. So I'm wondering why we did not discover X-ray weak sources at these intermediate redshifts before now. Was there a selection effect? Did people just not follow them up? I mean, like your redshift 5.5 guy, you know, it seems like we could have gotten X-ray measurements for those guys. So sorry about my ignorance about multi-wavelength studies of AGN, but can you help me understand that?
Yeah, so for instance, for this specific source, actually the lack of X-rays that was known before, already for quite some time, was one of the reasons why people, when they did not have this JWST data, but just ground-based coverage of some of the UV lines, did think that it's probably not an AGN. Yeah, so I think it's very possible that there are a number of sources and also of AGN, also at more intermediate redshifts, somewhat lower redshifts, that are just undiscovered in that sense, because we have been so used to using the X-ray detection as a clear signature of AGN. And then if you don't have the coverage spectrally, like in the object here, to then see the broad line region in the hydrogen and helium lines at longer wavelengths, then it might be very hard to identify these objects as black holes. There have been some works also in recent years already that look for some of these high ionization UV lines that we just discussed, like the nitrogen lines or helium-2 in the UV, to try and classify objects as AGN without this X-ray signature and without the coverage of the longer wavelengths. So I think it's a very good point that you're making, and I think it's very possible that there are some low metallicity objects at these intermediate redshifts as well that we are not aware are AGN, and if we now maybe use JWST to cover a different wavelength range, we might be able to discover much more of them.
Great, thank you.
Thanks for such a nice talk, Hannah. This is Priya. It's possible, right? These sources probably got misclassified just as star-forming galaxies, right? And not detected as AGN. It's quite possible that they got misclassified.
Indeed, yeah.
We have about another minute for questions. Any last questions or comments? Let me very briefly ask one. This is Peter Baruzzi. Should we be concerned at all about the mismatch between the models and the data in the emission line ratio diagnostics? In other words, we're trying to interpret the two spaces as AGN versus star forming or AGN, but then our models are not really covering where the data is covering.
You mean like diagrams like the PPT?
Some of the later, like 2 slides later, maybe. Like here, for example, on the right.
Yeah. So I think also for this diagram, but also actually for a more commonly used diagram as the PPT, it's been common that there are some regions that are extremely hard to actually cover and generate with the models. So similar in the PPT, these regions in the very top right have been notoriously hard to realize in the models. And I think, of course, it's good to be concerned about this and try to find out what could be the reasons why we cannot fully cover this. But of course, here we have the data that shows us what these sources are in the PPT. And so now in trying to develop these newer diagnostics, I think we can accept that maybe there are some spaces where we have not the full details within these very simplified models to fully model these relatively complex systems. But of course, there's still a lot of guidance within the models and a lot of overlap in the coverage of sources and modeling that I think this can still be extremely useful for us to identify AGN and star-forming galaxies nevertheless.
Thank you. One very, very brief comment from Rafa while Dale comes forward.
Hi, Anna. This is Raffaella. So thank you for your beautiful talk. So you mentioned that for some of the sources, you have signs of possible ongoing mergers or, disturbed morphologies. I don't know if anyone has already looked into more details of this, if you can quantify what is the fraction of these that could be ongoing mergers, and if these are somehow related to the properties of the black holes, such as the Eddington parameter that you derive.
Yeah, thanks, Rafa. That's a very good point. So I think for sure we can expect that if we have active accretion and merging ongoing, that we might have scenarios like described in several theoretical models to have gas that is more efficiently channeled onto the black hole, and therefore we might see the black hole in this growth and active phase. Now, for the fractions that you're asking for, I'm not aware at the moment that there are already some numbers out, and the difficulty with this is that, of course, we have some cases like this where we have the integral field spectroscopy, and so we have a near-come image. We can look at these blue faint blobs around them, or also like in the object here, and we can clearly, through the spectroscopic information that we have, identify that these sources are at the same redshift and are indeed satellites and ongoing mergers and interaction. Now, however, for many of the sources that I showed at the beginning, where you see this blue fluff around it, because most of them are observed with near-spec MSA, just with a slit on top of it. Let's see, maybe here this shows this a little bit better. So we have this slit on top of it. And so from imaging, we might see that there's something around this galaxy potentially, but without a spectroscopic confirmation, we cannot really say for sure that this is at the same redshift and therefore in interaction. And so I think this is what makes it hard at the moment still to gather sort of statistically significant numbers. And this is something for which we need larger samples with the integral field spectrograph, which now hopefully we're getting in the next year.
Thank you.
All right, let's all thank Hannah again.